Okay, well, thank you for having me today, Mike, and thank you for the introduction, Lawrence. It's a nice way to start the weekend. As they said, I am a PhD student at Lamont Doherty Earth Observatory right now, and I'm hoping to tell you a little bit about the research I do, and then you can ask me questions about it. So let me know if you have any trouble seeing my slides or hearing me throughout any of this. I'd be happy to stop and figure things out. But the title of my talk today is Investigating the Antarctic Ice Sheet Using Geophysical Methods. And as I said, I'm Caitlin Locke, and that's my email if you ever want to email me. Hopefully we'll be having our open house at Lamont in October this year, fingers crossed, and you could come and visit me there. Okay, so did my slide chain, you can see it? Okay, so here's a quick outline of the talk. First, I'm just going to tell you who I am, and then what I study, and then we'll jump into talking about the cryosphere, a little bit about climate change-induced sea level change, and then into ice sheets and ice shelves, and then some of the research I've been doing in Antarctica. So who am I? If you're from New York State, I'm from Mount Kisco, New York. I went to Fox Lane High School in Bedford, New York, where I first really encountered earth science. So shout out to Mrs. Waddell and Steve Kluges who were there. I took like the New York State Regents Earth Science course and then sort of just fell in love. Fast forward to undergrad, I attended Columbia University and I have a Bachelor of Science in Earth Science from there. And then fast forward again, I left for a little bit and worked in the diamond industry. You can ask me about that another time. And then came back to do my PhD in the Earth Science department there. I'm in the Polar Geophysics group within the Marine and Polar Geophysics division at Lamont. And and I'm probably graduating in December. That's the hope. So I have a lot to finish up in the next year, but it's like all very exciting. And so, what do I study? So my primary research interest is the cryosphere sciences. And within that, I'm interested in Antarctica and Greenland, and primarily Antarctica right now for my research. And these are just some fun photos. This is me actually at an unconformity, the Taconic Unconformity in New York State. It's great if you haven't been there. This is me in Antarctica, and then this is some pictures from Greenland and Antarctica as well. So I feel like you probably all know this, but just to review, where is the cryosphere? So it's primarily like the Arctic and the Antarctic. So, and I always like putting in that, you have polar bears in the Arctic and penguins in the Antarctic. They do not ever exist together. And what is the cryosphere? So it's places on our Earth where the surface is frozen. And that is sea ice. It can be land ice. That's glaciers, which is, I think, one that we more typically think of, snow, and then ice sheets and ice shelves, which I'm primarily interested in, and then permafrost. And then I just showed that this picture is from Greenland, and this is from Antarctica, and this one is actually in Tasmania. So we were flying to Antarctica. And so yes, so my primary interest is Antarctica and Greenland and their ice sheets. And something that is just important, I think, to set the stage for before we talk about this presentation is that an ice sheet is this big, thick ice mound, I could say, on top of bedrock. And it can be up to 2 kilometers thick. It's huge. And over long time scales, we like to think of ice as very still when we're looking at it in our own lives, but over longer time scales, it does flow. And that is why we study it. We're interested in the ice dynamics and the consequences of it melting over time. And I want to just have you look here. So I'm talking a lot about ice sheets, but something I'm also very interested in is the ice shelf, which is the portion of the ice sheet that flows into the ocean and begins to float. And these are very important parts of the ice sheet environment. So again, just like, how do we study the cryosphere? Like, how does my group in particular study it? And this hint I have is we use airplanes, ships, and satellites to do geophysics. So here, I'm just showing you a bunch of planes that I've used and my team has used to go to the Antarctic and Greenland to collect data. And my group is primarily involved in airborne geophysics. So we use airplanes and we put our instruments on the airplanes and we collect data. And so what are these instruments? So, and again, I just put like a plane, and then we have ships in the ocean, then satellites up in space. So we're interested in studying the ice surface, and here's like a fun video that I hope will play. And so we want to know what the surface of the ice is, and the primary instrument for that is LiDAR, which is light imaging, detecting, and ranging instruments, where they're sending out signals to the ice as we're flying and creating pictures or images of the surface of the ice, which is what this plane is doing in this video. Slowly it will become more and more detailed over time, and we get a picture of what the ice surface is for a certain like distance based on the plane height and the instrument we're working with. And then also, again, satellites now, there's specifically one that's a NASA satellite called ISAT-2, which is doing the same thing. It's collecting measurements on the surface of the ice. And then also we're interested in the ice thickness, which is this bottom part of the ice sheet, or you could think of it as the base of the ice sheet where it hits that bedrock. And to collect this, let's have a video. That pretty much said what I wanted to say, but we have radars on our instruments that are collecting data on the bottom of the ice. And what I find really interesting is that, we're able to collect data where that ice bedrock interface is. But once we have any water involved, that radar is no longer working, which is why I didn't highlight the rest of this seafloor in red. The radar just, it attenuates, it flatlines, it's unable to collect data there. So how do we get that really important measurement? Well, that's called seafloor bathymetry. And we primarily can get that also from a different instrument. So we get that from ships, which collect multi-beam data offshore where there is not ice. So if there's no ice, they're able to have multi-beam instruments on the ship and understand what the seafloor looks like underneath it. Also, the satellite, that same satellite that collects data about the surface of the ice, in really shallow areas, it can actually get through the water and get that bathymetry signature, but it's not as reliable. So the main thing we use currently, especially in Antarctica and Greenland, for this vulnerable space under this floating ice, where it's very important to know what the seafloor looks like, we use gravity meters, which is what is in this like couch-like looking or ottoman-like looking blanket on the plane with me and my colleagues Sean and Dave. So these are gravity meters, which are measuring the gravitational field of the Earth, and we can use that to understand the mass change underneath the plane and create maps of the seafloor, which is just like so amazing.
Excuse me for a moment, Caitlin.
Yes.
Do they have any instruments which are spectrometers, which can tell what the composition of the rocks are?
So yes, so that's like magnetometers. So and not on every season we haven't had a magnetometer on every season we've flown, but I have done a few, and actually I have a slide on it later. But yeah, so we're measuring the magnetic field of the Earth, and that can tell us about the composition of the rocks beneath the plane, which is very amazing as well. Usually it goes at the back of the plane. Usually there's like a little bit like of a tail boom that sticks out that were, I think, originally intended for finding submarines, but now we use it for science. So here's just some more of our groometers that we use. So this is the one that I showed you before, but in other times they're sort of on these racks in the middle of the airplanes. They always go inside the airplane, never on the outside. They are very sensitive to the cold and also the movement of the plane, so they need to be monitored more closely during flights. And then we've also had little ones like this on tinier planes, like these PA-31 planes or the Twin Otters. But I've been fortunate to, fly these and go on campaigns both in Antarctica and Greenland and Alaska. So again, we've covered where the cryosphere is, what it is, and how we study it. So why are we doing any of this? It sounds very cool, but there is like a real important reason. And my hint is sea level rise. So just to tell you right up front, we have this measurement called the sea level, or term called the sea level equivalent in our field, where that means that if all of the ice that's on top of Greenland or Antarctica were to melt today, what would the sea level rise equivalent be? So Greenland has 7 meters of sea level rise, or 23 feet. So if it melted today, 23 feet of sea level rise. Antarctica has 53 meters of sea level rise equivalent, which is 190 feet of sea level rise equivalent if it melted today. So that is a lot larger than Greenland. And that total, both together, is 65 meters or 213 feet of sea level rise. And that is why we care. Because Greenland and Antarctica are melting. They're losing their ice mass. And here's a video of where you can see the orange and red regions are where Antarctica and Greenland are losing ice. The blue areas are where they're gaining some ice or snow. And then the white areas are like unchanged. So basically it's zero. So as you can tell, as we're getting closer and closer to present day, the orange and reds are increasing. Especially you can see around the Greenland coast line, and then in Antarctica, it's primarily in what we call West Antarctica, right here, where it even starts to get very, very dark, and we're losing a lot of mass. And this is where in the news you're going to see there's actually a New York Times crew currently in West Antarctica going to that region that is melting. So this is why we care. And so let's just again look at global mean sea level rise. So here we're seeing a graph where you can see the sea level rise in blue, and then here this orange, the blue is from tide gauge data that we have from 1900, and then the orange is from satellite data when it came online in 1993. So as we know, sea level rise is going to impact millions of people worldwide who live in coastal regions over the next few centuries. And, sea level rise between 1900 and 1990 was 1.2 millimeters per year. And then between 1990 and 2018, it went up to 1.6 millimeters per year. And then between 1993 and 2020, it became 3.3 millimeters per year. And of this, 1.3 millimeters of this is due to thermal expansion, which is due to the warming Earth. Things are actually expanding thermally. And then 60% of it is due to this mass increase from ice sheet and glacier melt. So 60% of sea level rise is from the ice sheets and glaciers melting. So even just let's roll back at least to where I'm, one of the closest tide gauges near to me in New York City is in the Battery. And if you look over time, sea level is rising. And between 1856 and 2024, which is amazing, we have this data, the rate is at 2.94 millimeters per year, which is equivalent to about a foot every 100 years. So sea level change, and I'm saying change because it can rise and fall in different places, mostly rising, is due to both global and regional drivers. So The regional drivers happen to be the gravitational pull of the land itself, pulling water towards it. There's glacial isostatic adjustment, which is when, glaciers or ice sheets are melting and the land is rebounding, and other things. And the one I'm primarily going to focus on today are these global drivers of sea level change, which are the Greenland ice sheet, the Antarctic ice sheet, and glaciers. And as I said right before, ice sheets and glacier melt is contributing to sea level rise, and 60% of that is from them. And, right now, Antarctica and Greenland contain the majority of Earth's fresh water and, just have the potential to significantly contribute to sea level change in the future. And as I said before, this is 213 feet. And so between the two, they're both important to study. But I'm primarily focusing on Antarctica. And something I just want to show you here is that if you look here, the level of understanding with 3 pluses means high and a 1 plus means low. And all of these things that are contributing to like ice processes and our uncertainty in them, like halving of icebergs, the basal melt underneath ice sheets, and even the surface melt are like poorly understood processes right now. And that's why we are studying it, because we want to know more about how everything is working so we can make better predictions on what will happen in the future. And there is this IPCC report, the Intergovernmental Panel on Climate Change, that releases reports. And all of the work we're doing is in it, but now that I've just shown you, we have large uncertainties in the actual ice processes, which is why we're studying them. But those uncertainties are baked into these reports that are telling us how much sea level is going to rise and informing government decisions around the world. So, right now we're saying that global mean sea level change is possibly going to, by 2300, be 9 meters. But if we really are that uncertain about certain processes, is that closer to 65 meters? I mean, there's a lot that still needs to be worked out. So that is why we're here. So there's a lot of uncertainty in the ice processes. We know there's a lot of potential for sea level rise contributions. So let's go to Antarctica. Let's do this work. Let's study it. And so something just to tell you is that I'm focusing on New York because that's where I'm from, but you can see that here there are a lot of different cities that are named. But at least along the New York coast, sea level rise sensitivity is due to the Antarctic and Greenland ice thickness change, which is whether or not it's melting. And sea level predictions for different cities around the globe depend on the location of where the melting is happening in Antarctica or Greenland. And for New York, that happens to be the West Antarctic Ice Sheet. So right here, this is where the contributions to sea level rise in New York are going to come from. And from Greenland, they happen to be in the northeast portion of the Greenland Ice Sheet. And that changes for different cities. And this is actually a really wonderful website that I sort of put here, but it's located at the Jet Propulsion Laboratory at NASA. And they allow you to input your city and see where those contributions to sea level rise are coming from based on where that ice is melting in the world. And for New York City, I just said it is Antarctica, but it's a lot more than the contributions to Greenland. And I do like that it includes other areas of the world. So again, this was a motivating factor to why I study Antarctica, and in particular West Antarctica, right here, where we see that a lot of that mass loss is happening. So in West Antarctica, there's been accelerating mass loss, and this is particularly happening in what we call the Amundsen Sea embayment here and the Bellinghausen Sea, where they've lost 159, or they're losing 159 gigatons per year of ice. And how do ice sheets gain mass or lose mass? Let's just like review that. So you gain mass through snow accumulation, and then you lose mass through submarine melting or basal melt of the ice shelves. So in this very vulnerable region, and then also iceberg capping. It's about 50% of each in Antarctica contributing to this loss. And as I said, around Antarctica, we have these areas along the continent edge where ice shelves form, where this like grounded ice that's on bedrock begins to float in the ocean and starts to float. And these ice shelves are incredibly important in stabilizing the ice sheet through buttressing, which restrains the flow of this grounded ice from flowing into the ocean. So my analogy is, say you have a wine bottle like on its side like this, and it has a cork in it. That cork is like an ice shelf, and it's holding all of that wine inside the wine bottle. Once you remove that cork, all of that wine can flow out. So that's what ice shelves are doing. They're holding all of that ice on the continent, but when they break up, they allow that ice to flow into the ocean and contribute to sea level rise. Which is why we are constantly seeing news about breaking up of icebergs or icebergs breaking up, because it makes scientists really nervous about what is happening behind that ice shelf and how much that ice is then accelerating into the ocean. So mass loss underneath ice shelves is concentrated where warm ocean waters can access the area under the ice shelf and begin to melt it from below. So that is where my research is primarily focused. We can't send ships underneath ice shelves. We have tried to send submarine robots under ice shelves, but we're still working on that. They get lost a lot. So right now, the best thing we can do is use airplanes to understand and map this vulnerable region, where this bathymetry, or you can think of it as water depth or seafloor topography, controls water circulation under floating ice and the interactions between the ice shelf and the seafloor. So, over here you can see like when we have a seafloor topography that is quite, flat, or there are no barriers, it can let warm water just flow straight to the back of the cavity and melt wherever it can and wants to. But say there is some sort of like sill or, ridge of topography that can possibly block warm water going in, that is really good for the ice sheet and the stabilization of the ice shelf. But we don't know if they're there if we can't map them. So my research is focused on mapping the seafloor under ice shelves. So that brings me to some research that I've been doing. So this is a paper that was published last year on the Venable ice shelf, which is this tiny ice shelf compared to other ones, still quite large, in West Antarctica. In between, it's in the Bellinghausen Sea sector, right above the Amundsen Sea embayment, in this place that is melting immensely. So it's open access, so you can go find it if you want to, or never look at it again. And so if you're wondering, why did we do the Venable ice shelf? Well, it did not have a map of the seafloor, and we had collected data over it, so we should make the map of the seafloor, number one, which is great to do that. But again, what was really interesting scientifically is that it was actually behaving a lot differently than its neighboring ice shelves in the region. It was thinning extensively. The ice shelf was thinning over time, but it was not actually, oh yes, a hand. I see a hand. Oh, that's actually funny. Zoom did that to me. I don't want to raise my hand, lower hand. I guess I can't use hand motions. So yes, this ice shelf was thinning, but we weren't seeing this phenomenon called grounding line retreat, where it's known that when these ice shelves thin, the point where the bedrock and the ice meet starts to actually move inland. And that was not happening in this region, which was just interesting. But when we were suspecting that like this thinning was occurring because of that warm ocean water that was like getting into the subice shelf cavity, but we didn't know if that was actually true. And we didn't know what the seafloor looked like under this ice shelf because we had not been able to map it yet. So what we did is we modeled the seafloor under this ice shelf using the airborne gravity data. And that's what this paper is primarily about, and delivering that model to the community to use in ocean models and other studies. So here, I'm just going to show you right away, is our new map of the seafloor. And then this is what it looked like. If you can see the GIF going like before, this is what it looked like, very smooth. And then after, it's a lot more detailed. And this is just the difference in what we were able to provide from what was assumed before. Because there are people that are modeling these based on, say, a measurement onshore and offshore and just sort of like interpolating between. But there's a lot more nuance, as we know, to a landscape that's 80 kilometers long. So we were able to provide more detail in this region. And things that we were able to, discover were that there are these new troughs or deep pathways that are able to bring water to this grounding line, which is this line right here is the area where the bedrock and the ice are touch. We also, found, based on the depth of these troughs and the known depth of the warm ocean water, that water's flowing freely under this cavity and accessing that area where the bedrock and the ice are touching, which is where these circles are. And another interesting thing that we did discover is, we're looking for deep places. We also found some new places where the bathymetry of the seafloor was actually shallower than expected. So just a little bit about like how we did this. So I explained our method. We use airplanes. So these are two of the airplanes that we collected this data with. And these lines here over here are our survey lines. They were 10 kilometers apart. So, we're not having the most coarse survey. We're doing what we can. So 10 kilometers for this ice shelf was the best that we could do based on the conditions for flying. And this data was collected with this airborne campaign called NASA Operation Icebridge. It was a decade-long campaign, actually meant to help calibrate and bridge the gap between two satellites, the ICESat and the ICESat-2 missions. First one, ended, I think, earlier than they thought, and then the next one wasn't launching for another 10-ish years. So they put similar instruments on planes and just flew similar flight lines annually, and then they added other instruments like radar and gravimeters, which was really, really wonderful for the entire scientific community. So here's me with the P3 in Greenland and the DC-8 in South America, where we were stationed before doing these airborne campaigns. And again, on this plane, we were using radar to collect the ice thickness or the base of the ice. So I used that for this study. And then I used the LiDAR, the laser altimeter, to get the measurements for the ice surface. And then we had one ship track off the front of this ice shelf, which gave us an understanding of what the seafloor was in front of the ice shelf. So the multi-beam data. And then we took gravity data over this entire survey to help us understand and map the seafloor topography under the ice shelf. And then we also, as Mike was mentioning earlier, we did have a magnetometer on this survey as well, which has allowed us to understand the changes in the magnetic field and possible rock types when we were doing this model, which changes the density inputs that we put into our model. And then what we did is something called a gravity inversion, so where we take the gravity data and we're able to take it from like an unknown straightish line, slanted line from two data points. We're able to use the gravity data to create a more detailed understanding of what the seafloor is underneath it. And this is just an image of like one survey line in our models where we have our gravity data, which does basically mimic what the seafloor topography will look like based on the mass changes beneath it. So basically, when you're flying, if there's a greater mass, you're going to show that the signal is being pulled towards that mass. But if there's a valley, there's less mass, so the signal is less. It's being pulled less towards that. So similar like apple on a spring idea. And we were able to do that for the whole area. And this brings me just to something that came out of this project that I think is really fun and interesting, and it's sparked new work, so I wanted to tell you about it. So, for this study, we set out to map the seafloor, and we did it. And we now released that to community. We were like, great. But when you're writing a paper, most of the time, you want to also write an interesting discussion section that talks about what this means, like what you've now produced in this product, like why should anyone care about it other than that you mapped it and that's nice. Well, something that we discovered is that these shallow regions were actually a lot more interesting than we would have thought. So you can see here I've highlighted in like cyan. These are areas that were known to be shallow under this ice shelf based on other measurements, where there are areas where the ice is actually stuck to these higher points. And you can see that in satellite imagery. But what's interesting is that we now modeled and discovered a new bathymetric high that was unknown. And so we know that these high points can be actually attached to these ice shelves because they're so high underneath them. And we were just wondering, it's like, oh, is not that far from the bottom of the ice? Like, could it have been stuck to it in the past and be called a pinning point? So, I've just sort of described this, but here's a better like graphic. So pinning points are like local sub-ice shelf bathymetric highs where the ice shelf is attached to the ice base, like this here. And they're important because they provide this buttressing to the upstream ice flow. They help keep ice shelves in place because if you think more places where the ice shelf is stuck, helps it be more stable and less vulnerable to ice thinning. There had been another study that had used satellite imagery to actually track and measure change in these pinned areas over time, basically looking at, was the area above the pinning growing, meaning it was thickening, or was it decreasing, meaning that ice was probably thinning around it. And they were able to use these satellite images that go back to 1973 to create a timeline and history of this like thinning and thickening signature over time on ice shelves across Antarctica, which was an amazing study to run into. And they extended this record beyond what we currently knew. So what we did is we said, this is a very interesting study, and we have this area now that we know there's a bathymetric high. Let's look at the satellite imagery too and see if we see anything that this other study didn't see. So we took satellite images, particularly Landsat imagery, which goes back to 1973. And then we took our bathymetry model and what we knew about where this bathymetric high was, and we investigated whether or not this was a past pinning point. And so to spoil it, but yes, we discovered that it was, which was like really cool and had never really been, a pinning point had never been found this way previously, like using a model of the seafloor. So how did we do this? Well, what we did is we went back in that satellite image, which is a little blurry here, but you can sort of see there are these two lines. And then these are contours that I placed over where our bathymetric high is. So if you imagine it's like the mound. And then these crevasses are just right off the side of it. And what we believe is that they're actually forming below and then slowly going to the ice surface. So we identified these crevasses. And then we also noticed when we were looking here, we were like, oh, there's like a gap here where there's no crevassing, and then there's again crevassing all the way towards the ice shelf line. And if I can convince you that a bump hitting the ice would cause damage, that seems pretty feasible, that crevasses on an ice shelf near a bathymetric high are from being grounded or pinned. And then when there's no crevasses, that means it was unpinned and ungrounded, not attached to the sub-ice shelf bathymetric high. So we interpret these crevasses to represent grounding and ungrounding of the ice shelf over time. And to understand this further, what we did is we actually tracked the crevasses in the imagery. So we went all the way back to the first time we saw a crevasse, in particular this one in 1988, and then tracked it all the way to 2020 and how far it moved over that time. So it had a rate of 656 meters per year of movement within that time period. And then after 2020, it caps off. It's gone. You don't see it anymore. So if I just looked at our present day satellite image, I wouldn't have seen any of this. So I was really lucky that I did go all the way back to 1973. And so what we're proposing here is, you can see I've now stitched together this imagery. And we'll let it go to the beginning given, but we're proposing that this bathymetric high that we found has been thinning and thickening over time in the satellite record and before it. So here we're going to start back in 1973. You can see the crevasses, and they grow over time, and they eventually detach and then slowly move towards the ice shelf front and cab off one at a time. So what does this all mean, other than showing us that the ice shelf is thinning and thickening over time? Well, just to break it down, so we believe that this ice shelf, what we did is we used that ice shelf velocity that we grounded to actually date the crevasses that we saw in that first satellite image, because we can now measure this distance and apply that and then assign a date, essentially. So we believe that this crevasse here formed here in 1935. And then that means that this whole entire crevasse packet was stepped to this bathymetric high between 1935 and 1958. And then something happened between 1950 and 1970 where the ice thinned enough to detach from this high. And then again, something happened in 1970 where it regrounded and was attached again and creating more crevasses. And then again in 1988, it thinned again. And then from 1988 on, it's been ungrounded. And we haven't seen any further evidence of damage, which means that the ice shelf is still thin and thinning. So here, from this interesting study where you're just mapping the seafloor, we're able to essentially create a new method to understand ice thickness change on ice shelves in Antarctica, which, the previous study had just looked at the surface area of known places where it was stuck to the seafloor and how that changed over time. But we've now expanded that by saying crevasses can be used where there are known ridges or bathymetric highs to help us actually understand ice thickness change. And this is, so I tried to add our new interpretation into their schematic. It should be a little rotated. I'm working on it for a paper. So in the future, maybe we'll see a better one. But the idea is that, you can have a place that's stuck to the seafloor with, a surface expression, but you can also have a crevasse. And then eventually, as it's thin, this ice shelf is thinning, maybe that surface expression disappears, but a crevasse is still there. And then eventually, if it continues to thin, you're going to have no surface expression, and the crevasses that had formed when it was stuck to the seafloor are now down at the front of the ice shelf. And it's like a, it's left over from before. And I like to think of it as sort of it's not a tree ring, but it's similar in that it's a way to look in the past in a new way. So, from all of this, we were able to now say that there was thinning beneath this new westernmost pinning point at least 50 years ago in 1974, and along all of them, the other ones that were known at the same time. And again, just saying that we know that we were grounded on this ice frontfall at least 89 years ago in 1935, and then there was thinning between 1935 and 1958 there, and then it again grounded in 1970. What's interesting is actually at the same time this one was thinning, so there are some different ice dynamics happening here that we're figuring out. And then again, everything thinned so much that they were showing thinning signatures from 1988 onward. And I created this timeline just so we could sort of look at what was happening on the ice shelf. And then I also looked at this record of ocean warming and cooling in the Amundsen Sea and Bayman at the same time. I was interested to see if they overlapped. Or if I could, oh yes, oh I don't hear you. Oh no, I think you need to unmute yourself. I can't hear you. Are you saying Leo? I think you're still muted. Wonder if I can unmute you. I don't know if I can.
Okay, yeah. Okay.
Oh, there you
are you
okay.
also looking at the amount? Okay. Are you also looking at the amount of methane gas in the ice too?
You know, I haven't done that, but there are people that are taking a course and looking at that. That's just something that it's actually something I want to look more into in the same region, just to understand if anything overlaps. But I haven't gotten to ice cores yet. But there are a lot of people out there collecting them and looking at that. Just not.
I mean, because if you look at certain layers of the ice, you probably have more methane gas in certain layers than other layers of the Antarctic or greenhouse glaciation.
Yeah. Yeah, no, this is something that, you know, we sort of like made this discovery and we were like, oh, wow, that's very cool. And so now what I'm trying to do is to look at exactly that, like at other studies who have been looking at similar things to see if they align. And so for this one, at least on this slide, what I've only done so far is look at this like record of ocean warming along West Antarctica to see if there's anything happening with warm waters that would cause thinning or thickening. But I really do want to look into ice core data, so thank you for bringing that up.
Lamont doesn't have facilities to do ice cores.
No, we don't, which is sad. We have lots of cores, but none
There's a
that
place
are
out in
ice.
Colorado that does that.
Yeah. So maybe if I get into that, I'll get to go to a facility, which would be so fun. I would love that. Yeah, but so just, I guess to finish what I was saying here is that I looked into this ocean warming record that was from 1935 to 2015, and what I discovered is that in the time when we knew that the ice shelf was grounded but had to be thinning in order to unground and unpin from this bathymetric high in 1958, there had to be some warm ocean waters or something causing this thinning. And what was amazing to see is that there was this really large warming signature right before the ungrounding happened. And that actually is from following a major El Nino event that was between 1939 and 1942. And it caused warm ocean waters to actually flood the continental shelf in Antarctica around this time, which is why we believe that we see this unpinning at this time. So it was like really fun to like connect that. So hopefully I'll make more connections over time. And then something else that we did see though, which is there's also this, there was this thickening that we saw in 1970 to 1988, which actually was like a little different than what we saw in the ocean forcing. So that actually made us come to the conclusion that the thickening we're seeing just in this particular area in the ice shelf was actually due to like increased ice flow from like the continent. So that's just like there's interesting layers. There's like ocean influence, and then there's also the ice flowing in, there's atmosphere, there's a lot happening. So now we're trying to like figure out what's causing all of these thickening episodes that we're seeing. And so just like to show you what I'm doing next is that we've sort of discovered this new way to look for evidence of ice shelf thickness change over time using crevasses and ice shelves and known like bathymetric highs. So I am now using this method and scouring the entire Antarctic continent looking for these features. And I'm just going to show you quickly like 3 that I've found so far. So, I looked on the George 6 ice shelf up here, the Abbott ice shelf, and the Dotnet. It's an ice shelf where I've seen similar features where there are bathymetry models that I could confirm that there were bathymetric highs where we're seeing these features. So I again use satellite imagery and known bathymetry models from papers that have been published. And I was able to find and see these features growing over time. So this is on the George 6 ice shelf. So this is 1973, we have a crevasse. And then as we go through time, you can see the growth in these crevasses, which shows that the ice shelf was thickening and more damage was occurring or it was pinned at that time. And then there's thickening or pinned until 1989. And then in 2000, we can see that actually these crevasses are moving. So the thinning must have occurred. And they're slowly moving away from this pinning point. And then by 2014, they actually completely cap off. And then in the Eastern Abbott here, what I've done is I've sort of highlighted the contours of what are these bathymetric ridges. And we see nothing in 1973, but by 1988, you see damage forming on either side of this ridge. And over time, there is movement. It's very small, but there is movement between 88 and 97. And then over time, things continue to move very slightly to 2024. So it's actually really slow on the Abbott ice shelf, which if I just showed you 2 images, you might not believe me that they're actually moving. And then on the Dotson ice shelf, again, I'm looking specifically right here between 1973, as we go towards present day, you can see this one crevasse becomes 2, and then it grows over time and continues to grow until present day, and actually ends up connecting to a different pinning point. And so it was fun to be able to find, at least on these 3 ice shelves, different features. I'm also looking at other ones now. What I'm also now trying to do is to do the same thing where I'm looking back in time before the satellite era. So I've been able to assign dates to crevasses that are seen in that first satellite image. So again, deriving ice shelf velocities by tracking crevasses over time. I've been able to date the front of the Abbott ice shelf to 1844, which is amazing. I didn't realize that. And then on the Dotson ice shelf, there are crevasses at the front of the ice shelf I've dated to 1830 when they were formed. And that just shows that between 1830 and 1840 it was grounded. And then again, ungrounded, crevasses between 1844 and 1879, grounded again for a short period of time, ungrounded, and grounded again between 1902 and 1937, or grounded, ungrounded, and then grounded again. So this has just been very fun. And when I initially assigned these dates, I was like, wow, the 1830 and 1844, just I think I messed that one up. 1814 it should be. I was like, that's really far back, and I was like, that corresponds to the Little Ice Age, which was amazing if that is real. And so I did look into other evidence of the Little Ice Age in West Antarctica. So I'm, working through other studies and trying to see if I can make connections. And that's really it. So I just want to say, thank you for listening to me talk about my research. I'll hopefully be wrapping up this project. I have to graduate. So I'm wrapping this up this year and doing another one. So I'll have more if you want to check back in December. But thank you so much for listening. And I'll take any questions. This is actually one of my favorite photos. So we were flying down a glacier in Greenland. So you can see the rocks on the other side of the plane. It was amazing.
Wow. Thank you very much, Caitlin.
Yeah,
Very
thank you Thank you so much for having me. I hope it was fun. Yes, Lawrence.
I'll take the privilege of the host and ask the first question. Do we have enough ability to know what the bathymetry is underneath the ice and know what the effect would be if there's the melting of the ice in terms of flooding of the land?
Um, well, I will say that not every vulnerable ice shelf cavity has been properly mapped. So I would not say that we're in the place that we need to be to know everything about each ice shelf cavity. That's something we're actively working on, and that does involve going to the field and collecting data and then having people to model it. So, there are other people that are working on different ways to map it without having to go to the field, but I still think we have a long way to go to know exactly what is under each ice shelf. And even so, it's always, everything you do is a step forward. So even like with our model, it's, made off of 10-kilometer space data. Obviously, it would be nice to have more data. So there's always more we can be doing, more data we can be collecting to make maps more accurate. Yeah, and I think out there in the world, a lot of people just assume everything's mapped because, we have Google Maps, but we're so far from knowing everything.
Right.
I
Thank
don't know
you.
if that answered your question, but
Okay, everyone can unmute and ask questions now.
Lawrence.
So I got a couple of questions, but I won't hog it. So first of all, are we able to know what the shape of the underside of the ice is that's floating above the water?
Yes,
Okay.
yes,
So
yes,
is
which is
it
great.
possible? So is it possible? And by the way, first of all, I should have said this amazing discovery and amazing presentation. And I hope the New
Oh,
York Times will interview you and that you'll get on TV. You're an amazing, amazing scientist and articulate. It's
oh,
really,
thank you.
really terrific.
Thank you.
So, um, underneath, is it possible? Have you considered whether or not the underside shape maybe sometimes was deeper in some spots, and that's why the ice shelf pinned on the peaks? So have you looked for correlations between the shape of the ice getting, basically caught?
I see what you're saying. No, that's a great question, and I have not done that. So that's something that I think I've been so focused on the seafloor that I've been less focused on the bottom of the ice shelf. But that's like a very good point because you would think that that could be there would be a reason for things to be thicker where they were stuck.
Right.
And it could be either they're stuck to the seafloor or maybe they're in a more protected area of the ice shelf that was like less vulnerable to the ocean waters melting them. But that is definitely something that I will think of now when I look at these because that's a great point. So
Because
yeah,
I mean, the diagrams always make it look like it's flat, but if it's irregular, it's
and it is.
possible, that there's something that was deeper about the ice that got stuck. So another question I has is the correlation. Way at the beginning of your results, you talked about how unusual this spot was, is that there was less retreat
Yes.
in this area. Have you have you considered any correlations between the average height of the seafloor in this area versus the average height in other areas? So that basically, are there
Yeah.
more barriers to the warm water flowing in?
Yeah. Yeah. So it's like yeah, exactly that. It's like a combination of things where the seafloor here happened to be deep enough to let that warm ocean waters in, but there's actually an ice shelf right next to it where the seafloor is shallower. So those warm ocean waters actually were less able to affect and melt the ice. So that was something that we came out of the study just looking into that because we were just like, what is this major difference between these two, and they're so close to each other, and it does have to do with the seafloor depth and also actually the thickness of the ice. So if the ice is already thin and the warm ocean water won't be able to actually melt it. So it's in some ways the ice has to be like thick enough to like see that change too. But that's something we're looking into. It also does have to do a lot to do with like pinning points and how they're contributing to buttressing. So yeah, everything is so detailed, and every time I look at the whole map, I get overwhelmed by how different each ice shelf is. But it is like very interesting and cool, and we're trying to find correlations across West Antarctica right now, and we are finding small ones, which is really interesting.
So basically, it could be like the height above the sort of underwater seawall
Exactly.
and
Yeah.
the depth of the water. Like that difference is where the warm water could flow
Mm-hmm.
in. So that
Mm-hmm.
distance is,
Yeah.
no.
Yeah. Yeah.
Okay,
No,
cool.
exactly. And then a lot of that too is just still like the continental shelf is still very unknown in certain areas around Antarctica just because there's a lot of ice, so it's hard to map. There are a lot of cruises actively trying to go down there, not, but, more and more data would be so helpful for exactly this, because there are places where, in papers where we have, because there are known troughs that are on the continental shelf, where we know that warm ocean water is able to then get onto the continental shelf. But then there's like big question marks in the middle of some of these being like, maybe it's going this way. Like we just have not been able to like send someone there to collect the data. So yeah, we definitely need more science in the area.
Thank you.
Yeah.
Other questions, please?
Yes, I have a question.
Yes.
So, it seems like the system is entropic in the sense that, like, you were measuring the western part of Antarctica, and if that part melts, shouldn't the continent or the landmass of Antarctica and Greenland, shouldn't they raise up like a lot of places around the world where once the ice melted, that the land raised up?
Yes. Yeah. So that's actually my advisor is actually trying to look right now and to see if there's any evidence of uplift in the areas that we know are melting. And there are people there, a lot of other people's trying to look at that same thing. They did just like take out a lot of the
Because
GPS.
a lot of parts of the earth. I mean, you look at parts of Europe or whatever. That once the ice melted, a lot of these places, because of the weight of the ice, and if the
Yeah.
ice is
Yeah.
2 miles thick in
Yeah.
Greenland, I
Mm-hmm.
mean, once that starts melting, the land
Mm-hmm.
should start
Oh
raising
yeah.
up. The same thing should
Yeah.
start happening in
Yeah.
Antarctica too.
Yeah, well, and that's actually there's something I didn't really mention when I was talking about this, but we talk a lot about sea level rise, but there are places experiencing sea level fall, and Greenland is one of them. There's a whole other study that people in my group are working on. It's called Greenland Rising, because it's exactly that, where the ice is melting so much that the communities that are living there are seeing the seas fall around their towns, and their like ability to fish is now disappearing, and they have to go further and further away from their houses, so they're relocating towards the ocean. And it's like a different problem. It's like globally there's more sea level rise, but there are these local areas like Greenland is also in Alaska where communities are experiencing the opposite because they happen to be so close to the ice sheet itself. Where the land is rebounding, and it also has to do with the mass of the ice. Like mass attracts water. So it's like the water is actually attracted to the ice sheet itself, and as it melts, the water subsides as the land rises. So it is nuanced as well. So we do expect Antarctica to rebound and sea levels to fall locally around Antarctica, but that means there's still global sea level rise. That water is still out there in the ocean.
Not sea level rises, but the land raises up. The land raises up
Oh yeah,
underneath Greenland, and
yeah,
because of the weight of the ice,
yeah. Mm-hmm.
on top of Greenland, which is very thick, and the land on top of the ice in Antarctica, the same thing will
Yeah,
rise because the plasticity of the
yeah,
ice will just flow out, and these
yeah,
lands
yeah,
will raise up. I mean,
yeah.
this is uh,
No, I know. Actually, I'd had a slide. I wonder if I deleted it. That showed just that. Oh, that's too bad. I should have. should have kept that. I wonder if I can find it. Oh, maybe it's here. Here's see all my edits where my stupid plane was moving. Oh, come on. Where is it? I don't know if I still have it. Oh, here it is. Oh no, I don't have it. I was hoping. Anyway, but I had a fun figure somewhere, and I'm trying to see if I could get it back. You can see.
Well, that was a pretty good diagram. We had that big ice
I know.
glaciation.
Oh wait, here it is. I'm just kidding. I'm gonna unhide. Do you see this now? Yeah. So exactly this.
Yeah.
Yeah. So.
Yeah, rebound. Yeah.
Yeah. And so here's what I was talking about, where there's the ocean that's attracted to the mass, and then as it melts, it actually does fall. And then depending on whether or not you're on this peripheral belt or not, the landscape is also changes. Yeah, there's a lot happening. So it's a very interesting system study. I see that Mary has a question. Did you want to ask? Oh, I think you're muted. Oh no.
Okay, yeah, I think.
Oh, no, you're still muted. No.
Oh.
Mary?
Yeah.
Oh, there you are.
Hello,
We can hear you now. Yes.
Oh.
Oh, no, for some reason when you turn your video on, you mute. But then when you have your video off, you unmute. That's... Oh.
You hear that
There.
now?
Yes, I hear
Hey,
you.
I think you're answering my question. I just wondered, is this some crazy meniscus? Is it gravitational? You're just answering the question of why it would be that the land and the ice shapes so affect the retreat and the coming back to water. And thank you. This is so clear and so helpful. And I teach middle school, and sometimes it's kind of interesting but useless to come to these events because I can't really bridge the gap between a seventh grader and you guys. But some of the stuff we actually did in camp last year, we calculated the mass of Greenland's ice and then translated that to how much water rise we would get. And it was rough calculations, but it was still doable math. We got 20 feet, which, okay, it's probably not accurate, but it's still enough for them to see that this is math that can be done, which is, even from a young age, important for them to know. So I appreciate it, and I love the resources on the ice shelf. I see you got a YouTube thing available too, so I really appreciate that this stuff is available and useful for me as a teacher, especially in my labs and summer camps. So appreciate that.
Yeah, I'm so glad. Yeah, I can, at some point I'd be happy to share links, even with just the nuance of sea level change and rise or fall. This is a great, I think you hopefully can see this is a website on NOAA where you can go and see the rate of the sea level change, whether it's rising or falling, globally. And then also just in the United States, which is really fun because you can see, it's going down, fall is in Alaska, and going up everywhere. And you can click on every single arrow and it will show you the rate of sea level rise or fall over time. And that's just super fun. I actually had my, was a teaching assistant for an intro or science class, and I had them do this for their hometowns. And that was a fun little exercise just to bring this home and have it become more personal and not just an abstract thing you're thinking about. So I'd be happy to. Yes, Lauren?
Can I follow up to Leo's point? Have you considered that rebounding of your discovered peaks also in your models?
The answer is no. But it is something, and I think West Antarctica, there are a lot of people working on that to see if there is rebound. And I just didn't incorporate that into my models. I think mostly because it's just the data wasn't available at the time, but it's something I want to look into because, if rebound is occurring, that would influence the being pinned or not.
Right. Right, another factor. Although,
Yeah, I
doesn't
know.
rebound take a long time though? Maybe it's over too
Exactly.
long a time frame
Exactly.
for
Yeah,
effect? Yeah.
exactly. I think the time scales may not totally match up within the one that we're able to like study. Obviously, it would be great to go further and further back in time, but right now we don't. At least I don't have the resources for what I was specifically looking at. But that doesn't mean that, you know, there will be more discoveries in the future, hopefully. Yeah.
Any more questions?
Thank you.
No, thank you. No, and I just like to say, like, I, you know, obviously like encountered earth science for the first time, like in school, like public high school, and it like drove me towards this career. So you all are, you know, just like appreciate all of you for doing what you're doing. It's, I think, more and more important to be teaching earth science today than any time in the world. So I just like, you're doing the hard work, and like, you know, I remember when I was in school, you were allowed to like skip earth science because if you did well enough in other sciences. And I don't know if that still is the case, but I remember just being so alarmed. I was like, why would I skip a science? And I'm so glad I didn't. And I just think that like earth science is so important, and we all know that, and we all love it. So, so thank you. This is like it's really nice to meet you all, and really like you're always welcome to reach out. I'm usually just sitting in my office puttering away. So, yeah. Thank you, Mike, for having me.
No, just don't do it on Monday mornings. The
Yes.
staples,
Yeah.
the
Not this
staples
Monday for
available.
sure. And then also, yes, we do have our division meeting on Monday mornings. If you want a bagel, stop by. Yeah, thank you.
Okay, thank you very much, Caitlin.
Thanks so
Good luck
much.
with everything.
All right.
Thank you so much,
Okay.
everyone. Have a great
Okay, I'll let you all
weekend.
know when this gets posted. And thank Chris for editing and posting.
Thank you, Chris.
Okay, bye
But
all.
thanks so much.
Yeah,
Thank
thank
you.
you.
All right.
Keep
Bye.
up the great
Thank you.
work.
Thank
Bye.
you.
All
Bye,
right.
everyone.
All
Thank
right.
you so
Ciao,
much.
ciao.
Bye.